So you have a chance to leave the room if you want, but that's on you if you stay, because I'm going to talk about whatever I want. And what I want to talk about today is cloud native. And the reason I want to talk about cloud native is that about a month ago, another speaker was ill, and I got called to talk at another conference, which was called Cloud Native Day. So I had to write a talk, this one, kind of, I changed it. And I didn't give it at the end, because when I got to the venue, the original speaker also came in. So it was like, okay, fine, awesome. Now I've got to talk, and I've got nowhere to talk, so yeah, so you're screwed, basically. So this is a talk about the move that we had from the PETS model to the cloud native model of today. And I'm going to run through the short history of what happened in the last like 10 or 15 years. 1 second, thanks. And just try to keep up. Try to follow. It's going to be weird, it's going to be funny, it's going to be awesome. Feel free to interrupt or shout or whatever. So, when you give a talk about something like cloud native, which is kind of a buzzword, first thing that you do is you go to Wikipedia and you check what the hell is cloud native, right? What is it? So I went to Wikipedia and was like, okay, native cloud applications, blah, 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 refers to a type of computer software that's native, blah, 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 blah. Really vague. Really, really vague. Like, this definition doesn't actually tell me what cloud native is. I don't know if anyone knows what it is. Certainly I don't. So, okay, like if the source of human knowledge, which is Wikipedia, doesn't know what to tell you about cloud native, like this is really bizarre. And it's one of those two situations. Either everyone knows what it is, it's like too obvious to explain, so you don't need to explain it, or it's something that no one actually knows what it means. And at this point, they're like too afraid to ask. It was like really kind of weird to get to a conference that is named Cloud Native and go to people and ask, like, what is this? So, yeah. So, apparently there's a Cloud Native Foundation. I don't know if you heard about it. They have a website. A lot of awesome companies like Google are members of it. So I went to the website. It's like, surely they have an explanation of what Cloud Native is. They have a GitHub repository with, specs and such. So I went to the GitHub repository, and I went to the Cloud Native definition version 1. And yeah, this is excerpts from that spec. Scalable application in a modern dynamic environment such as public, private, and hybrid cloud, which is awesome, but it doesn't tell me what cloud native is. Still, I don't know. So I read further, and somewhere in the middle I found this. Containers, service meshes, microservices, immutable infrastructure, and declarative APIs exemplify this approach. These techniques enable loosely coupled systems that are resilient, manageable, and observable. So I highlighted the important words. So now we get kind of a sense what characterizes cloud native systems, but it's still a bit weird. First of all, because manageable, like I've never heard of a system that claim to be unmanageable, right? So it's kind of weird, but yeah, let's just go with it. We've got some hints here. Let's roll with it and see where we go with this. So going back to the presentation and the story. If we want to go through the history of the cloud native evolution and how we got to those types of systems and understand what cloud native is, we probably want to start 15 years ago with the systems we had, what we call the PETS. And if you don't know the PETS versus cattle model, basically the idea was that the systems we had were pet systems that we cared for and we tended to them, and every system had a name, every server had a name, and if that server had a problem, we would go to that server and we would fix it, and we would, feed it and care for it and be very nice to it. And then we transition to this model where we have cattle, lots of servers, and if one of them is sick, we just shoot it in the head and replace it with another. And if there are vegan people here, I'm sorry, I didn't make up this analogy. Yeah. So that was the theory, at least. So the systems that we had 15 years ago looked something like that. We had a bunch of servers, physical servers usually, sitting in a data center somewhere and connected through a switch, top of the rack switch or whatever, and a network, like a network router and a firewall, and then it was connected to the internet. And on those servers, we deployed some code. Awesome. And we had a database that stored the data, and it was all fine and great and worked perfectly, kind of. And this kind of system has a lot of merit to it. It has a lot of advantages. It is manageable. It's very easy to manage such a system. And the way it was manageable, the reason it was manageable, it was because it was tightly coupled. Tight coupling means that everything affected the other parts of the system almost instantaneously. So it was very easy to understand cause and effect in such a system. And the downside of tight coupling is that if you have a problem, if something breaks, the other parts of the system also break very, very fast, which is also kind of an advantage because everything is very predictable in such a system. But the way you handle reliability of such a system is by making the parts of that system very reliable so that they don't break very often. So the way we achieved reliability in that kind of system is by having a stable environment. And remember, this was a physical infrastructure, so it was very easy to achieve, say, a stable environment. You had your own network, which usually was pretty reliable, and you didn't have to share it with anyone. So, you knew that you're getting the full bandwidth and everything, no noise. And you knew that the disks, you had all of the IOPS because no one else was using them, and so on, so on, so on. So the way that we got stable environment is because we had control over the infrastructure. We had control over the data centers, we had control over the network, we had control over the power lines, we had control over the hardware. But this all broke down when we went to the cloud, right? In the cloud, we still had the same architecture, same high-level logical architecture, but the servers were now all virtualized, and the network was virtualized. And in this type of environment, a lot of the assumptions underlying this architecture were violated because we no longer had control of the network, and we shared the resources with other companies. So a lot of noisy neighbors and that kind of stuff. During that time, we still had, if you look at the host names of servers, you would see something like that. Like you would SSH into a server and you'd be on application server, whatever. Because normally you only had one application server. It was on monolith at that time. And of course, the thing that changed was suddenly on the cloud you had unreliable networks, you had noisy neighbors, and so on, and so on, and so on. The environment was no longer stable, and we had to somehow cope with that. So we had to change the architecture, we had to adapt. And this led to a slightly similar, but also a little bit different architecture. We started having multiple components of each component. Suddenly, instead of having one virtualized server, we had a few, maybe in an auto-scaling group. So maybe you had 3 application servers, 2 databases for reliability, a master and a slave, and so on, and so on, and so on. And if you look at the host names, this is the time when we started seeing server names like this. It was like application server number 142. Presumably, there were like 140 other servers. Yeah. And this is why. So yeah, this worked. And at some point, people started using auto-scaling groups, so the number of servers was no longer constant. Sometimes it was 20, sometimes it was 5. You get the idea. And this went on for quite a bit of time. And also it had consequences. So think about this. When the number of servers start to change, also the IP addresses change. So it no longer made sense to put IP addresses in configuration files. So we needed stuff like service discovery and DNS and configuration management and so on, so on, so on. But also network topology started to change. Now, if we go back to that diagram, we still have routers and switches, but they're all virtual. Now, what does a virtual subnet or a virtual segment mean? Because from a network topology standpoint, do you actually care about subnets if everything is virtualized? Not obvious anymore. And of course, we had data conflicts because we had multiple databases now. So we started to deal with distributed systems, which made everything a lot harder. So what did we do? Of course, we went to the age of cattle. And you know that we changed to the age of cattle because of the host names, right? Now you have more than one application server and you can kill it if it's misbehaving. So this is the time where our mentality started to change. We started changing the way we do stuff, the way we manage our clusters and our services. Next thing that happened was we started putting code in multiple places. We no longer had monolith. Because once you have a distributed system anyway, and you have data conflicts, it makes sense to split the code as well. It allows for scaling your developers, having multiple teams work on different services and integrate them, in the network. Your system is already network heavy anyway. It made sense to split the data to multiple databases and so on. So we started seeing systems where you have your code deployed on multiple clusters of multiple services. And the host names reflected that as well. It was no longer application 23 because you only had one application. Now you had like Appy Muppy or whatever because you had like 10 applications or 10 services or even more. So microservices, yay. It was a great idea and it had no problem whatsoever, right? Yeah, a couple of problems. For example, this diagram, also known as the Death Star diagram of microservices. The problem when you have a lot of microservices is that it's very, very complex. You don't know what is talking to who, in what order, everything shifts. It's very complicated to track. If you've got, let's say, like Wix, 700 microservices, and they all talk to each other, just the number of possible paths is insane. And if you have thousands or hundreds of thousands of services, you can't even calculate that number. It's too big, really ridiculous. So yeah, new problems that we had to deal with, very annoying. So the age of microservices. The idea was that we would have semi-autonomous components that are usable, that we could just connect and rewire at will, very, very easy. It's all loosely coupled, meaning that if you have a problem in one service, it doesn't necessarily affect immediately the rest of the system. On the downside, it made problems a lot harder to detect and deal with. So monitoring became quite a challenge. And from the point of view of one microservice, other microservices are a black box. You only talk to the API of that microservice. You're not allowed to know what is going on inside the database or the data store. You're not supposed to look. Just have to cooperate with other microservices. It's all driven by APIs. And so we continue to evolve. And at this point, another interesting thing happened. Actually, two interesting things happened. First of all, look at the host names again. This is when you started seeing the transition from host names like this one, app whatever 23, to host names that had instance IDs. Now this seems like a very subtle change, but it's actually very, very interesting. Why? Because app 23 means that, at least conceptually, you think there are 23 servers, or at least 23 servers. How many servers do you have of this?
No idea.
You have no idea, which means that you don't want to know. We stopped caring about the number of instances that we have. And this is fundamental. This is when we started transitioning from cattle to something else. Another interesting thing happened. We started deploying code everywhere. So if you're like me and you're using a lot of services, you start to think about the fact that Google Drive can run code. They have something called GScript, which is somewhat similar to JavaScript, but it's not. And that's a whole different story. But you can run code on Google Spreadsheets or Google Docs or whatever. You can also run code on Twilio or Salesforce or whatever, Zapier. So you end up in this weird situation where you have code everywhere, not necessarily on Amazon or Google or Azure, whatever cloud you're using, but just everywhere. And it talks to a bunch of other clouds and a bunch of other services using HTTPS. And what we get is the internet. And it's very interesting because suddenly you have code deployed everywhere, not just inside your data center on your microservices. Okay, that's interesting. You also notice that people stopped caring about the network. Most systems that I see today, if they have VPC, they have like one or two subnets, one like the private subnet and the other one is like the public subnet, and maybe they have a few private subnets because Amazon forces you to have one subnet for every availability zone, but that's about it. You don't care about subnets anymore. Why? Because network topology that is completely virtual and doesn't reflect any physical structure is only interesting for access control rules, right? But access control rules, when you have 700 microservices that talk to each other, you just can't manage that. You would have 10 or 20,000 rules in your firewall. It's completely unmanageable. Okay, so we don't care about that anymore. And apparently not about slides either. 1 second, okay, cool. So, okay, now we have a bunch of code that's running outside of our cloud on a bunch of SaaS. This is the age of SaaS that we live in today. And yeah, the hostname changed to reflect that. So you take a look at the production systems of companies, big companies working at scale, like Wix from Israel and maybe Amazon, not from Israel. And you find that production changes rapidly all the time. For example, at Wix, production changed every 3 minutes on average. And if you're talking about Amazon, they deploy code on average about every 7 seconds. So what does that mean when you're talking about your production environment? It's like production? Which production environment? What are you talking about? Right? Because it changes all the time. You can't talk about the production environment in a meaningful way or the staging environment in a meaningful way when it changes all the time. And if that's not bad enough, you find out that you don't actually have a production environment, not in the sense that we used to talk about it, because there is no one production environment, right? For example, think about the fact that every client talks to potentially a different data center. And it could be that you have one web page that is executing multiple AJAX calls to a backend, and every component in the page talks to potentially a different service on a different data center that uses different machines and different versions. So you can't really talk about, about bugs and recreating bugs in a meaningful way when every single transaction uses different code potentially. Now, if you think about A/B testing, for example, at Wix we had at any given point more than 200 active experiments. And an experiment means that potentially you use a different code path or potentially a different service even for the same transaction. So the exact configuration of the specific transaction depends on which experiments you're participating in. So if you have 200 experiments, the number of possibilities is basically the Cartesian product of those possibilities, which means that we're talking about 40,000 possibilities when you have 200 experiments. So in a sense, you have 40,000 production environments, not one, when you have experiments. And I haven't even talked about personalization. Personalization, by definition, means that every transaction is unique, right? So once you understand this, you realize that you don't have a production environment. You have production environments, plural, and lots of them. Every transaction in such a system is unique and non-repeatable. There's really no way to reproduce that transaction because it depends on a state that constantly changes very, very fast and actually exists only for that single transaction. And this is where you start to go like, okay, now I have a problem. Because none of my monitoring tools reflect this. They just tell me that everything is green or red. What does that mean when you're talking about millions of transactions that have different behaviors and actually use different code? Not obvious, not really obvious. Okay, this also means that staging environments are worthless because they can't be useful to reproduce something that is by nature not repeatable. So at Wix, for example, almost no one used the staging environments, and it made sense. So going back to the diagram, we have a bunch of servers running a bunch of code, and then something else happened. The database itself became a cloud service. So it might be, RDS, just putting my SQL or Postgres on the cloud and then making it manageable, but that might also be something more fundamental like DynamoDB, a database that is completely hosted by Amazon and talks to you by HTTPS. And that's very, very different because it's essentially a public utility service. It's not your database in any sense. Everyone uses DynamoDB, the same DynamoDB that you're using. So your data is also, it's not shared, but it's only logically separated. It's on the same physical hardware. There's really no difference. Okay, that's cool. And the next obvious step would be, of course, if the database is a cloud service, maybe the compute nodes should be cloud service as well. So you move your code from servers that you used to manage or containers that you used to manage to maybe ACS or Kubernetes in the cloud or maybe even Lambda. So your code suddenly runs on this completely abstracted cloud. So you no longer have compute nodes. You don't even care about server names anymore, right? Even if they had IDs. All you have now is a transaction ID that is mapped to some anonymous container somewhere in the cloud that you don't even care about. And it comes and goes. It might live for a few seconds, it might live for a few minutes. And at this point, you don't even kill the kettle anymore. It dies anyway. So that analogy completely breaks down at this point. And one day you find out, after you completed your journey, that all that remained is a bunch of clouds running a bunch of code and has a bunch of data. Might be on DynamoDB, might be on S3, might be on a different cloud storage that also speaks HTTPS, which is in essence the entire network, the entire internet. But that firewall still remained. And it's really strange, because if you look at this diagram now, the network, we don't care about the virtual switches. And everything runs on public utility services that talk to HTTPS, like Lambda and DynamoDB. So what is that firewall protecting even? Like, is there a difference between in and out? I don't see it. So maybe we don't need the firewall. Because the cloud is inherently public. Think about this. If you have VPC, you think that you have a private network. It's a virtual private cloud, right? But where's the management interface for the VPC? Where's it hosted? Yeah, exactly, on Amazon.com. And it's public, and will always be public. So every notion of privacy that you have depends on one API call from the public internet. So the cloud is inherently public. VPC doesn't mean anything anymore. It's just the VPC, from a technology perspective, is a tunnel. It's a network tunnel on top of a public cloud, on top of a public network. And you know what else is a tunnel on top of a public network? HTTPS. So essentially, when you think about this, you reach to the conclusion that HTTPS over the public internet is actually more secure than VPC, because VPC is not encrypted. Okay, that's interesting. So you end up in an architecture like this, where you have just a bunch of clouds and a bunch of data stores talking to each other over the public internet. And this is basically the cloud-native architecture that we arrived to after 15 years of evolution. And it has a lot of consequences, because this system is very, very complex. It has a lot of moving parts that is hosted over a public network that you have no control over, and might be even hostile from a security standpoint and reliability standpoint as well. And it's also dynamic, it changes everywhere, because once you don't have control over the infrastructure, I have no idea when Amazon is going to make some deployment on DynamoDB or Lambda or whatever. So I take it as granted that everything will change and be dynamic all the time, even if I myself don't change it. The network is changing, the internet is changing all the time. And this is the age of germs. This is where we move to a new analogy of how we manage our servers. It's not cattle anymore, it's germs. Just a bunch of cells, like in biology. So we turn to biology and biological systems to try and learn something about how we manage this new world that we evolved to. And basically, when you look at your body, you see a bunch of autonomous cells, semi-autonomous cells that are cooperating. And you're alive, it works. So yeah, that must be good. Those cells are self-organizing. If you put those bunch of cells, they will immediately start creating structures that can do useful stuff like breathing. And they are surviving in an uncontrollable and sometimes hostile environment. And the fact that they do that is because we're standing here and talking. And one of the interesting things about cells is that they constantly die and they reproduce, constantly. Statistically speaking, every one of us has replaced all those cells probably 4 to 5 times from the time you were born. You don't have even a single one of the original cells in your body, but still the structure remains. You're still alive. So basically, this is the kind of systems that we want today. And with cattle, you kill the sick cow, but when you're talking about germs, We don't even understand what seek means because there's no clear definition when you're talking about a system where every transaction is unique and have a slightly different behavior. You cannot even define what a seek cell is. It's very, very complicated. Everything that you talk about in monitoring when you're talking about such a system is statistical. We only care about statistical macro level stability anyway. And by the time you check one of the cells, it's probably going to be dead and be replaced by another one. And oddly enough, in Lambda, you would find that there's no metric that tells you how many instances of Lambda existed at any one point at any given time, because you don't care anymore. And the pricing model also reflects that. You don't pay for concurrency in Amazon. And neither do you pay that in any of the other cloud providers, because presumably you don't care how many concurrent instances you have. And there's no way to catch a specific instance of Lambda and debug it because it just dies after it's done. So everything changes. And the way to manage that is to turn to a different model. And we have those kind of models. They're called complex adaptive systems. And complex adaptive system is a system in which a perfect understanding of the individual parts does not automatically convey a perfect understanding of the whole system behavior. And this is very important because if until now we imagined that if we understand how servers and services in our code operate, we can understand how the system in general operates, this is no longer true. First of all, there's no way to understand how the public utility clouds work because we're not exposed to the internal workings of those clouds. But even if we did, in a complex adaptive system, even if you knew exactly how all the parts behave, you could not understand the system as a whole. So we just need to give up on that concept. And that means that we have to change the way that we look on system management and monitoring and all of those stuff that are related. It's a brave new world that we have to adapt to. And by the way, this is known as the Hand of God cloud. It was taken over Madeira, Spain in January 2016. Look it up, really amazing pictures. Clouds. So we have new challenges. We need to learn how to observe and do monitoring in a world that has dynamic and keep changing all the time, and it has a lot of information. If every transaction is unique and individual, we have to now gather and analyze data about every single transaction. This is a lot of data. This is why monitoring is becoming such a big problem, why it becomes a big data problem. We need to manage numerous semi-autonomous components, sometimes in the millions. That's a lot of processes. We need to understand a loosely coupled system, which is very, very hard. We need to learn how to control a system that is nonlinear and chaotic. And everyone who had a system like this break down can tell you that it doesn't break in expected ways. It breaks in very weird ways that you cannot predict. How do you do security when you're talking about a system that is inherently public all the time? All of its parts are inherently public in a hostile environment because the internet, as you know, is not a very nice place. And every time you put something on the internet, it's immediately DDoSed. So yeah, that's weird. But the concept of resilience, the concept of having a reliable system, that changes as well because all the parts die all the time and they're being regenerated all the time. So it only makes sense now to talk about resilience and reliability when you're talking about the macro, when you're talking about the overall system. And again, the monitoring systems that we have that tell you that this service is either green or red no longer make sense because when you're talking about a system like Wix, you always have, no matter when you look, at least 1% of errors. And it's normal. It's normal to have that, and there's nowhere around that. So the definition of good now becomes something completely different. So it's very fortunate for us that a lot of smart people thought about those problems very, very long time ago. So this is Mark Borges. And Mark Borges is the father of promise theory, but also of modern configuration management. In 1998, he wrote an article called Computer Immunology, which was the basis of CF Engine, which was the original configuration management tool, which no one uses anymore. And he talked back then about macro-level stability and convergence, meaning processes that work to converge to a specific state that you define. And you as a programmer or you as a system administrator would define that state and write the code that converges toward that state. And this is how you get macro level stability. But this requires continuous active maintenance, meaning the constant reprovisioning or the constant cleaning and fixing of all those components that run. And it's a very interesting topic, and I highly suggest that you read about it, because if you think about those systems that we're going to have in the future, without those types of ideas, it's going to be very, very hard to build them. Luckily in Israel, we have a lot of companies that try to help those problems. Some of those companies are being supported by Aleph. A lot of those companies are not. I just put a dump of those companies here of some of those companies here on the board. There are a lot of other companies as well that try to help with those things. And we at Aleph try to help companies and organizations to transition to this new world. So thank you very much. And by the way, if you're looking for a job, we have a website that has jobs from all of our portfolio companies. So thank you very much.